Hi everyone, we're back here for part two of related rates, and I presented this question at the end, so hoping that you took a shot at it. I'm going to read it again. Also, I should have said this in the first video, but I highly recommend you write down all of these things in the video just as if you were in class. There's a lot to be said about the action of writing and how it engages the brain. It's an active position to learning versus if you just listen. Certainly you can get something from that, but that's a passive learning experience and doesn't engage the all the functions of the brain as if you were writing it like you were in class. So here we're really starting off with you know with word problems, and there's a couple of sentences to copy over. Even so, I strongly recommend that you do it, and the materials just gonna sink in just that much better. So, okay, anyway, here was the problem. A rock is thrown into a pond, creating a circular ripple. If the radius of the ripple increases at 5 feet per second, how fast is the area of the circle changing when the radius is 20 feet? And I gave you this hint. It talks about the area of a circle, it talks about the radius. So recall that area equals pi times radius squared. So what we'll do is using that equation, we're going to take the derivative of both sides with respect to t. So if we take the derivative of a with respect to t, we can see that as simply dA over dt. On the right side, well, the 2 comes down in front, drops to a first power, and because of the chain rule, we then need to multiply by dr over dt. Okay, so we've got our related rates equation. We've got our two instantaneous rates of change for the area and the radius. Once we have that, then we're going to identify what's the question asking, and then we'll plug in the numbers that we got to match everything up correctly. So what's really happening? Write that question: how fast is the area of the circle changing? What's the instantaneous rate of change of the area? That's dA over dt. How fast the area changes. And they tell us some other parts. When the radius is 20 feet, so when r is 20. And prior to these things, they had said if the radius of the ripple increases at 5 feet per second, the instantaneous rate of change of the radius, dr over dt, they're telling us is 5. So we're going to plug these values in. Maybe I'll go about to here. We're looking for this. We know r is 20, dr over dt is 5. And simplify that, and we got it. So 200 pi when we're done. And if you really want to go the extra step, what are the units of dA over dt? And it turns out they're feet squared per second. And it's kind of cool how this works, and you start to see the usefulness of this notation for the derivative. What's the units of area? Well, feet squared in this case. What are the units for t? And maybe by now you figured out t probably represents time. And that's absolutely right. And here the unit of time is the second. So area over time, feet squared per second. That's how fast the area is growing. 200 pi feet squared per second. You could even multiply the 200 and pi and round your answer as a decimal. Nothing wrong with that either. Okay, so we got it. As the radius gets bigger, the area is increasing. And there we have it. At that moment, the area is increasing at 200 pi feet squared per second. Okay, next, I want to show you guys my steps for any related rates problem. Okay, not all the steps are always going to apply, but in the most difficult problems, all of them will. And I'll tell you this one about the area of the circular ripple. That's about as easy as they get. And the reason being is because actually these first two steps are quite simple, and the derivative is actually quite simple. But I'll just start. Number one, in general, we're going to need to make a drawing. Now, for the circular ripple, really wasn't necessary. We can picture that circle. I think we can visualize that pretty well without drawing it. But in the problem we're going to do next, we're definitely going to need a drawing before we do step number 2, find an equation relating the quantities. In the problem we just did, the equation relating the quantities was area equals pi r squared. They talked about area, they talked about radius. We needed to know how those were related in an equation. I put a star next to that step because it can be that this is the most difficult. Just getting that equation, obviously that's key. You can't do anything until you have it, and it's based on your drawing a lot of times, so that can be the most difficult part, just getting the equation. Okay, then step 3, once you have the equation, take the derivative of both sides with respect to t, and t will always represent time. Of course, any kind of rules for derivatives could come into play, right? Product rule, chain rule is going to apply to all of these with the implicit, right? And then number 4, once you have the derivative, identify which derivative they're looking for in the question, and then plug in the other known quantities appropriately to get your answer. All right, let's go on to one that's a bit more challenging. So I'm going to show you guys just a little bit of it at a time, just like we were in class. This is a great problem. Imagine a 12-foot ladder leaning against a vertical wall, or maybe a house. So we've got it leaning up like so. And here's the situation. I'll try and get it all here. The top of the ladder begins to slide down the wall. So that top of the ladder is going to start to lose grip on the wall, and it's going to start to slide down. Very dangerous. It slides down the wall at 1 foot per second. So the question is, how fast does the base of the ladder slide away? Obviously, as the top of the ladder slides down, the base of the ladder is going to start to push this way. How fast does the base of the ladder slide away when it is 4 feet from the wall? So at the moment it's 4 feet away, how fast is it sliding out? This one we're going to have to round 2 decimal places. Okay. So step 1 in our related rate steps, make a drawing. So we've got a kind of a drawing to work with, but we'd like one that's maybe a little simpler. So I went ahead and drew this. So kind of simplified version of my ladder. I know that ladder is 12 feet. The top of the ladder starts to slide down. The base starts to slide away. So how are we going to go about this? Now, it's probably really tempting, right? They said when the base of the ladder slides away, when it's 4 feet. So at the end of the day, that's going to be, we're going to know the value of that length. But here's the thing. At the moment, it's changing. So we don't want to give this a numerical value, a fixed value, because that distance that's in motion. So I'm going to call that length right there x. And in a similar way, I'm going to call that length right here y. I give them variables because they're in motion. They are changing. And it probably, maybe it goes without saying, that's a right angle in the corner. Okay, so once we have our drawing, now the question is, can we connect x and y in an equation? Do we know anything from math, anything from our history, anything that we've learned in math that will connect x and y in this drawing in an equation? And if this was class, I would pause here and see what you guys thought of. But since it's not, I'm just going to tell you, we know the 3 sides of a right triangle. Pythagorean theorem tells us this. x squared plus y squared equals 12 squared. Okay. And all right, yeah, so we got it. That's how x and y are connected in an equation. That is likely the hardest step in this problem. From here, we're going to take our derivatives. So I know I'm going to take the derivative of x squared with respect to t plus the derivative of y squared with respect to t. And we actually did that very example at the beginning. Then I need the derivative of 12 squared. But 12 squared, well, that's 144. And the derivative, in any case, it's a number. The derivative is 0. Okay, so this is great. I've got my derivative equation. Now, I'm going to look back and think, which of these rates are they actually asking me about? So it says in the question, how fast does the base slide away? Well, am I talking about dx over dt or dy over dt? And well, the base, that's the x. This is what we want to know. How fast is that pushing out this direction? Really, that arrow is sort of like that's the dx over dt. How fast is that moving? Well, if this is what I want to know, I must be able to figure out the values of x, y, and dy over dt. So let's think here. Do we know the value of x? Do they tell us? And yep, they sure do. When the base, is 4 feet from the wall. So at the moment that x is 4. Obviously, x is in motion, but at this particular instant, that's what we're asking about. Okay, do we know what y is? You know what? Go back and read that slowly. They don't tell us what y equals directly, but we can figure it out. If we know we're talking about the moment that x is 4, we should be able to figure out y at the same moment. Turns out we need to go back to the original equation. So maybe kind of to the side, I know that when x is 4, 4 squared plus y squared will equal 12 squared. And, you know, in a couple of steps, I can figure this out. Y squared, if I subtract 16, will be 128. So I want the square root of 128. Now I could simplify that, but I'm going to end up rounding my final answer anyway. Let's just keep it as square root 128. So when x is 4, at that same moment, y is this. Okay. Do they tell me dy over dt? And yeah, they do. The top of the ladder begins to slide down the wall at 1 foot per second. Okay, great. Now, here's the thing. It's really tempting to just put dy over dt equals 1. But it turns out it's not quite that simple. If the top of the ladder is sliding down, isn't y shrinking? Isn't it like it's getting smaller? If I say dy over dt equals 1, that'd be like saying y is getting bigger. It's increasing. It's positive. But if y is actually getting smaller, then I need to say dy over dt equals -1. Now that's very subtle. That's easy to miss. But that could make a difference when we solve. Okay, so when we put them all in, I know 2 times 4 dx over dt, 2y is square root 128. I wrote an equal sign there. I did not mean to. That's a plus. dy over dt is -1, and that whole thing equals 0. So if I continue, right? That'd be negative. If I add that over here, I'd end up with 8 dx over dt equals 2 square root 128. And when I divide, let's go ahead and just round this right now. I got 2.83 when I round. And if we pause and think about units, well, what are the units on x? Feet. What are the units of time? Seconds. There we go. 2.83 feet per second at that moment. I think we're going to pause here. Been talking for a little while. I've got one more example when we come back. See you then.